Okay, good afternoon, I guess. This is our last real lecture. The next week we have 2 slots for project presentations. I would like to record them, just I don't have any strong reason, just to have an example. Certainly it would help me, I guess, if I go over them, but I don't have to. So if you prefer to not be recorded, just send me a quick email or tell me in person. I will just declare that group not recorded, and we'll skip them. We don't have to disclose who you are if you want to do it semi-privately. Otherwise, Aaron will be here to record. So we can record some of the groups and not others. Or we can skip the whole thing if many people don't want to be recorded. I was also asked to talk a little bit about the project report. I'm not sure what to say. Yoon, I think we gave a page limit, right?
I can remember.
Whatever page limit we gave, if you cut it in half, that'll be better. Make it less is more, as famous saying. What I'm looking for in the project itself, and therefore also in the report, is evidence of understanding what the course was about. And what the course is about is how to convert linguistic intuition and understanding of language into statistical profit. So statistically sound methodology, but it's informed by what we know about the domain of language. So what I'm looking for in the project is not just throwing techniques blindly at the problem, but making some kind of argument for the linguistic appropriateness or the linguistic source of your motivation or your hypothesis or whatever. And then, now that you have a linguistic inspiration or insight, convert it in a methodologically sound way into some kind of method. Whether it actually worked or not is a bonus. If it worked, it's certainly very nice and it's a bonus. But if it didn't work, it's okay if you demonstrated in the process that you did all the right things.
How would we know if it works or not?
You should be able to find a way to tell how well it works. I mean, how well will it work in our tests? Is that what you mean?
I mean just like verifying depth and report numbers in the report. So we clearly cannot.
Oh, you can't include the final test results in your report.
Okay, so
that the TAs will provide, right?
Is the domain of the test set considerably different from those of the training and the development set?
I don't think so. I don't remember anymore, but I thought it was the same, yeah. Does it say that it would be different? There may be, at some point we had a variance where you test on something that's the same domain and one that's that's different, deliberately to see the difference. I don't remember if we included it or not. Do you guys remember?
Well, I asked this question of Pauza actually, and it was answered as, well, it is actually, on the project page, it says that it should be like very similar, including the distribution of sentence lengths or something.
Mm-hmm.
And the number of test examples, because we also worry that if you have like 10,000 examples, then software will be slow.
Yeah. No, all this is right. The number would be similar. The distribution of length would be similar. Think about it mostly as a fun thing, as much as you can. I know it's hard to think of it as fun at the end of a semester, but as long as you show reasonable understanding and you don't make huge errors that show a lack of understanding of basic statistical methodology, you should be fine.
So what's accuracy do you expect?
I'd rather not give you a number to go towards, but just do the best you can. Fatima?
We were given 2 sources of data in the project page. One was explicitly referred to as training data. Those were 500 real and fake articles. And we were also given a trigram language model and the 100 million words news corpus. So it wasn't clear why these were given. Are we expected to generate additional test data from those? Or
additional test data? No, but you can use it as resources, as a baseline, as whatever, and you can use any external data you want. Any data, any package. Don't reinvent things for the sake of reinventing them. Use existing packages, existing tools if they're appropriate for you, and same with data.
So why is this model provided, language model provided different from the original model that generates the fake document?
It's claimed to be very similar.
Very similar, but why is not exactly?
Maybe because if it were exactly the same, the problem would be too easy.
So I think this question was that since we are given the training data which contains 500 real documents and 500 fake documents, then we also have a 1 million word corpus from which we can generate more real articles and more fake articles. So are we supposed to do this?
If you want.
Okay.
If you want. Does that make sense?
But will that be unfair? So if some groups have more training data and some did this and have more training data, some didn't do and we have those 1,000 articles.
I don't understand how it would be unfair if anybody is free to do it if they want.
Yeah, but suppose two groups have exactly the same algorithm. One did this and the other didn't.
Okay.
And or one did less and the other did more. So
Okay.
one group has more data than the other.
Okay. Why is that unfair? I mean, they're free to
In this way, will we be driving the groups to just generate tons of data?
if they think that's going to help. Data is.
I don't know. Right?
Maybe there's something I don't understand here that we can talk about later, and if so, I'll post a correction very quick.
Yeah,
but
I think just encouraging them to generate more data is not helpful in the sense of statistical insight or linguistic insight.
well, I'm not sure I agree. Generating more data may be, in some situations it may help a lot, in other situations it doesn't. So it is a statistical consideration if generating more data would help. One could also argue that if you have a model in your hands you can generate unlimited amount of data from, maybe you're better off just using that model as is rather than generating data from it. I mean, somehow using it instead of generating data and then using the data to train something else. I'm not hiding any big secret. I'm just thinking out loud. Let's talk right after class. If there's something that I don't understand, I will correct. But I don't see a reason to restrict anybody from anything. And remember, the competition is not the most important thing. The competition, you're going to get glory and chocolate. I mean, not necessarily in that order. I mean, the important thing is use your knowledge, use your understanding, show that you know how to do it. It's the closest thing to the real world that we have here. So if somebody had an unfair advantage, even if they did, okay, so they got chocolate.
How it is unfair if people work to generate this additional data?
I'm sorry?
How come it's unfair if people work to generate this?
Yeah, I don't understand why it would be unfair. But I'd like to cover some more topics today. So let me get off of that and talk to you separately.
The other question is, how would you actually generate? I mean, you could generate fake articles, but how would you generate real ones?
Just take that from the concept that they are.
They aren't divided by articles. It's just running text.
Oh, okay.
You don't know where one topic ends and another one begins.
Yeah, that's true.
In the real world, you don't have rules, right? So whatever you can think of. And if you think it's going to be useful, try it.
Yeah, and
Yes.
on that note, it's also true that the model provided is not the exact same used to generate the fake articles,
Mhm.
so it might not be as much of an advantage as you think it is.
It could be.
So is that the reason why the exactly the same model is not provided?
Well, I answered before that one reason at least is that I think it would make it too easy. I deliberately calibrated the difficulty of this to be open-ended, and I can tell you a secret that not a big secret, that the longer the test thing, the easier it is to classify, right? So the shorter ones are really, really hard. Very hard to do much better than random. The longer ones are fairly easy and fall somewhere in between. In fact, you could do an analysis of error rate as a function of length. That would be nice. Okay, so we have 2 full topics to finish. I mean, 1.5. One SVM to finish, and then I wanted to talk to you about one other kind of model. So we'll do it necessarily at a relatively superficial level, but I want to do it anyway to just get the concepts across. So we were talking about how we might capture semantic coherence, semantic modeling, how we might even represent semantics. And one way of representing semantics is when you impose your semantics from the outside. When you come into a domain and you know that the articles are going to be about baseball or football or war or politics or this or that, and you come up with a list of any number of topics, and you manually label the different examples with the topics, and the topics might be hierarchical, and there might be a flat class, but you come with the preconceived notions of how many they are and what they are. The other way of dealing with semantics is to let these categories or dimensions of semantics emerge from the data. And that's what SVD tries to do for us. So the only starting assumption is that semantics manifests itself at the superficial level or at the surface level of the language with combinations of words, combination of word choices. So that is something that's reasonable for us to accept, that in a particular topic like baseball, you know it's baseball because of the words that are being used there. And in fact, you can show that if you scramble the words of a document, people have no problem knowing what the document is about. So that's kind of proof that there's certainly enough information in the choice of words, regardless of how, in what order they come or what the exact logical content is. Just the collection of words and maybe how many times they occurred each tells you pretty much what the topic is to a fairly fine granularity of topics. So if you make that assumption, but we don't make a further assumption of what the topics are, we don't come from the outside, we're asking in a large collection of documents, if you represent each document by a bag of words, by just a listing of all the words and how many times they occurred, are there natural groupings? Are there natural directions along which the documents can lie? So an extremely simple case would be that most of the content words fall into distinct classes. Like if it's baseball, then all these words occur and none of the others. And if it's football, then all these words, none of the others. So it's like a partitioning of the words. And then it's very simple, right? But in the real world, it's not like that. In the real world, topics are related to each other and they're aligned with each other and there's noise. A good analogy for that would be, oopsie, if you have data in 2 dimensions and if it falls either along this dimension or along this dimension, it's very easy to tell which dimension it came from. So this would be one class, and this would be another class, class 1, class 2. But in the real world, there would be several problems. One problem would be that there's noise. So it's like it falls into like some kind of cluster. And the second would be that the variance in the 2 dimensions would not be necessarily the same. So maybe this one varies only a little bit. And the third one would be that they may not be orthogonal to each other. So if you put them together and all these complications together, you might get something that looks like this. And now you have to imagine it in 3 dimensions. Think about the Milky Way, our galaxy, which is a big spiral thing that's hanging in space in some angle. Angle relative to what, I don't know. But what's important for capturing the distribution of stars in the galaxy is the realization that there are some principal axes or principal components to this, and that this is one of them, and this is the second one going in, and the third one would be the thin one. So this has to do with rotating this ellipsoid, aligning it with our natural XYZ coordinate system. And it's easy for us to do visually, but if you just get a large file with the coordinates of each one of these stars, it's not obvious to you how you do that, but there's a way of doing that. You can do it with principal component analysis, PCA, principal component analysis, which is an algebraic technique for discovering the main components along which all the distribution lies. Okay? Principal component analysis is appropriate when you have unlabeled data. When you have just data that you want to, that is distributed, so you're looking for a density estimation, and you want to get a handle on the main dimensions in the space along which it's distributed and how far it is in each one of them. In the case of our topics, we have a slightly different problem. What we have is we have a mixture of documents and words, and we're trying to find underlying relationships such that every document could be thought of as either single or small number of components of pre-existing combinations of words. Okay, so every document would be maybe a component, maybe a mixture of three topics, three elemental topics. So it would be some component times this set of words, and some component times this set of words, and some component times this set of words. So that would allow us, if we had the right definition of the words, would allow us to represent every document very succinctly by just the three components, or the indexes and maybe the amplitudes of the three components. So in other words, it will allow us to create a basis function. Those of you who took linear algebra know what basis function is. We will have a set of basis functions. Each one would be a distribution over words. And every document could be represented by a combination of the basis functions with some weights on the combination. So this document is 70% about baseball, and 20% about football, and 10% about legal proceedings. If somebody gave you the basis functions, if somebody gave you the distribution of the elemental topics, it would be fairly trivial to represent every possible document, every candidate document, as a combination of them. The opposite is also true. If somebody gave you, how would that go? Maybe that's a less good intuitive interpretation. Let's leave it at that. But the problem is that nobody gives you these basis functions, so you have to discover them yourself. So our goal is to discover a way of grouping the words into combinations that are not necessarily orthogonal, so they can be overlapping and aligned, but create combinations or directions in the m-dimensional space of words that allow us to represent each document by a relatively small number of components. Okay? So now let me tell you what SVD does. So we start with a big matrix, which we will call X. This matrix, along the rows we have words. Word 1 through word, we'll call it M. We also called it V in the past for vocabulary. We call it M because SVD literature likes to use M and N. And here, along the top, we'll have document 1 through document N. So it's an M by N matrix. The typical entry is Wij, corresponding to word I and document J. And as we discussed last time, it will be some weight that takes into account how often that word occurred in that document, but also how informative that word is with regard to how many documents it tends to occur in. It's a TF-IDF measure. It could be some other measure. It could be some real number. And we're going to decompose this matrix. So there are lots of kinds of decomposition of matrices in linear algebra. This is one of them. I want to emphasize that the dimensions here could be very different, m and n. First of all, they're very large. So m, we said, is typically 10 to the 5, 100,000 words in the vocabulary. And n is typically 10 to the 6. At least this was in the past when I designed this lecture. But now it's 10 to the 7, 10 to the 8. You know, then the size of vocabularies does not grow that much, but the size of collections grow a lot. And what I want to do is to break it into a set of three matrices. And this is what it looks like. This goes from 1 to m, just like this one. But the number of columns is small. Call it R.
Professor, maybe you should use N for words and M for documents as last time you used.
Did I?
Yeah.
Oh, darn. Because in my notes I use M. I'm sorry. And also in Wikipedia, they use M by N matrix. I'm sorry. You can just call it number of documents and number of words. All right, this matrix is going to be, okay, this is R by R. And this is going to be R by N. So first of all, from the rules of linear algebra, you probably remember that when you multiply matrices, the indexes have to match. So you have an m by r times r by r times r by n. This gives you an m by n final answer. Second, if r is very small, if you count the number of numbers here, they're going to be much smaller than the number of numbers here. So if this is 10 to the 5, and r is, let's say, 100, you have 10 to the 5 times 100, plus 100 times 100, plus 100 times 10 to the 6. It's much less than 10 to the 5 times 10 to the 6. So we're actually passing this matrix through a bottleneck. We're representing it, we're actually compressing it in a sense. We're representing it by a smaller number of numbers. So it shouldn't surprise you that we cannot do it exactly. So this is going to be an approximate. If we allow R to be as large as the minimum of m and n, then we can do it exactly. But I don't want to do that. I want to reduce it to much smaller. So I may start by having R being very large, at least conceptually. And let me tell you what these matrices do. So this R matrix is a diagonal matrix. There are entries only here. These matrices you can think of as consisting of rows where every row is associated with a particular word. Associated with word I. So this is row I. And similarly, each column here is associated with document J. So there are n documents, n columns, and there are m rows, one for every word in the dictionary. The SVD decomposition has the following properties. These columns are orthonormal. Meaning they are normal. That means their length is unity. Their norm is unity. And they're orthogonal to one another. Well, no, that's impossible. Can't have so many. These are orthonormal. You cannot have so many orthonormal columns when you have they're only of length 100. You can think of this matrix as operating on the space of words and rotating it so that the combinations of words that tend to occur together are along the axis, the natural axis of the space. Similarly, you can think of this matrix as operating on documents and rotating it so that natural combinations of documents, documents that are about the same topic, are aligned along the same dimension. You can think of this matrix as giving, these are numerical values that you can choose to arrange in descending order. Lambda 1, lambda 2, lambda 3, and so forth. Some of them might be 0 or close to 0. Under general conditions, the SVD decomposition is unique up to permutation of the rows and columns. And if you choose to represent these in descending order, then there's a unique set of values here. So you might get, I'm sorry, this would not be unique. Let me take it back. These will not be unique. These will be unique up to permutation. And if you choose to represent them in descending order, then they are effectively a canonical or unique representation. These will not be unique because there are many ways of rotating spaces. If you do this, if you insist on it being completely identical, then R must be at least as large as M or N. But in that case, you didn't gain as much. So what you can start doing it that way and then look at these values. They tell you how important these dimensions are, how important the different topics that you found are. And you can decide to chop it off, let's say at 100 or at 200 or anywhere where these values become very close to 0. And now this becomes an approximate representation. But it's not just approximate, it actually has good theoretical properties. It is the closest possible representation, or think about it this way, it introduces a distortion, this representation. If you re-multiply these together, you get a matrix that's not exactly the same as this matrix, but it's similar to it. And if you look at the distance between them in L2 space, you can prove that this decomposition gives you the closest possible approximation in L2 space. So these are theoretical properties. Now in practice, what this does for you is it generates almost out of nothing, without prior linguistic knowledge, it generates natural topics. It generates topics based on which words tend to co-occur with which other words, and which documents tend to occur with which other documents. It also allows you to take a new document that you have never seen before and to add it here as if it were an additional column. So you can take the document and map it to its component weights. So you can call that a pseudo document. So in other words, you can take a new document and map it into the space, to the lower dimensional space of 100 features, and represent it by its components in the 100 features. You can do the opposite too. You can take some arbitrary given set of components, of topics. Let's say you want a document that is 30% about baseball and 20% about US-China relationship and 15% about this and that. You can take that and convert it into a distribution over words. So now it gives you a unigram that corresponds to that particular combination of documents. Remember that all of this is in the unigram space. There's nothing here. That's all bag of words model. There's nothing here about which words follow which specific other words. It's all about a mixture of different unigrams. But what's sort of new about it is that the particular mixture, so the particular individual components are determined automatically to be such that they capture as well as possible the document word correlations in your training data. SVD has been known for many years. You should read about it in Wikipedia or in any statistics textbook. Lots of properties. It's used for lots of things. It was first introduced to language in the 80s by a group out of Bellcore. And they gave it the name, Bellcore is Bell Communications Research. It was one of the early split-offs of Bell Labs. They gave it the name latent semantic analysis. It became very useful in information retrieval, and then it became almost like there was like a religion war on it, because the people who believed in it and people who did not believe in it. There have been a variety of attempts to make it more sort of rigorous, sort of statistically justified. There's something called probabilistic latent semantic analysis. Wherever you see LSA, it's basically application of SVD, of this decomposition, to Word document co-occurrence matrix. Anybody who works in information retrieval can tell me if LSA is in vogue or not in vogue these days? Anybody here works in information retrieval? Really? A little bit? Okay, have you heard LSA?
I don't really work with that at all.
Okay. So maybe it's out of vogue.
Is it used outside of information?
Yes, but not as SVD is used all over the place by signal processing, electrical engineering, all of that.
Oh, I mean, like in
But
NLP.
in NLP, yes. So the one example I'm very familiar with is the paper that I put online by Jerome Bellegarde. And that is for improving language modeling. So he goes about it in a very roundabout way, but I think it did provide a nice improvement. It was a form of semantic smoothing. Kenton?
Yeah, I think my understanding at least is a lot of more extensions of this are used, right? So you can view something like LDA as having like a document in word frequency matrix like this, but doing more complex clustering on it, right? So I think that's what's more used today.
Right. So by LDA you mean latent Dirichlet allocation, you don't mean linear discriminant analysis,
Yeah.
right? So be aware there are two LDAs lurking here. The old and classic one is linear discriminant analysis. It's a discriminator method designed by Fisher 100 years ago. That's if you have lots of inputs and you're trying to learn a discriminator by a set of lines. Latent Dirichlet allocation is something that uses the generative story similar to the one we described here, namely that you first choose components and then you mix words based on the components you choose, with the added complexity that the number of components is not predetermined. You can add another component. A new topic may come about. So yeah, I think what's used now is more probabilistic versions, more than. So this, this is not really probabilistic. There's nothing probabilistic in this description. This is more algebraic. You have a matrix and you're trying to represent it in a smaller space. You're trying to find a lower dimensional story that is a good approximation of the big dimensional story. Because if you think about it, this matrix is 10 to the 5 by 10 to the 6. It's huge, okay? And it's mostly zeros. So staring at it will not help you much. You're trying to find a way of bringing it down to what's going on. What are the small number of things, around 100 of them, that are recurring themes here? And the problem is that every document is not one recurring thing. It's a combination of some subset of these 100 recurring things. That's what SVD does for you. There were other comments? Yeah.
We actually were using SVD not in the context of latent semantic analysis, but we have higher order matrices, and we were using basically tensor SVD to reduce dimensionality of representation of words in a distribution space.
Okay.
So
It seems a very reasonable way to me to think about semantics. Malcolm?
It's still, I know like people in my lab group who have done like dimensionality reduction experiments on like noun phrase and word co-occurrence vectors, or matrices to condense words which are used as features into like a smaller, like 100 feature space using PCA.
Okay. So again, PCA, the difference in PCA is that there are no labels there. It's just representing which words. The main difference, a lot of similarities between PCA and SVD. The main difference is that in PCA, there aren't multiple topics or multiple flavors. There's just trying to represent the distribution of things by a small number of dimensions along which most of the variance happens. So in the galaxy case, most of the variance happens along this dimension, and the second one is along the second. I mean, you know that if we looked at this from above, it would look like this, right? That's the Milky Way looked at from quote unquote above is something like an oval. So the most variance happens along this axis. Second most axis varies along this axis. In fact, I think this is what, 10,000 light years? Anybody here who knows some astronomy? I think this is like 10,000 light years, and this might be, I don't know, 2,000 light years. And then if you look at it from here, which is how I'm looking at here, the width of the donut is much smaller. So it's almost a two-dimensional object, but it's not quite two-dimensional. If it were two-dimensional, it would just be an ellipse. But it's a little thick, so it has a thickness. So that's the third dimensionality of change. So you can represent the entire Milky Way by these three dimensions and how much variance is along each one of them. Okay? That's the essence of PCA. These are the three principal components of variation. In SVD, you have the issue of correlation between words and topics. Every document is a combination of a bunch of topics with some weights, and every topic consists of some distribution over words. And so therefore every topic is a collection of, every document is a collection of topics, which itself is a collection of words, but nobody tells you in advance what the underlying distribution of each topic is. So you're finding it automatically. When you find it automatically, it doesn't necessarily agree with our prior intuition about what a topic is. Sometimes it will, sometimes it won't.
Although in both cases, aren't you using the same method in PCA and singular value decomposition?
I don't think so. So PCA, you are rotating one matrix. You're basically taking a matrix, and you are asking yourself what rotation of it will produce the highest variance. And then you fix that direction. What direction of rotation produce the highest variance? You fix that direction, eliminate it, and then do it recursively. I don't believe it's the same mathematical process.
Isn't the key that you multiply? Like you would take this matrix and then multiply it by its inverse, or not its inverse, but its transpose.
Transpose, yeah, it's Hermitian transpose. So this matrix, let's give them names. We usually call them. I call them topic. Has some document, but I'd like to use what they use in general. Oh no, they call it TSD. So T, S, and D star. So what is star? Star is the Hermitian transpose. So if you have a matrix, M star is M. How do you do conjugate and transpose? Is transpose and conjugate. How do you Right. It is. Okay, in this case it'll be just for real numbers, it'll just be M star is M transpose. In general, Aij star would be Aj transposed. Again, I forget how you conjugated. How do you conjugate? So, I'm sorry? Bar. Thank you. It's been a while since I did physics. So, in a complex matrix, you would transpose it and conjugate it, namely convert A plus IB to A minus IB. This is the general form of SVD. In our case here, it's SVD over a real number, so it doesn't matter. It's transposed. All right. We have a half hour left, so I'd like to move to what I'd like to finish this course with, which is, in my opinion, maybe the nicest example of marrying together language and statistics. So we haven't really done much linguistic until the last few weeks, because we had to spend so much time worrying about the fundamentals of smoothing and sparse estimation and clustering and get the basic concepts. But the first time we got reasonably close to languages is when we looked at context-free grammars. And context-free grammars are much better linguistically, but they, stink as serious competitors to n-grams in the statistical sense of perplexity, cross entropy. So really the best thing we could do is if we can combine the power of both. So combine the fact that context-free productions are much better, much more reasonable, intuitive way of looking at language with the statistical strength of n-gram correlations. And furthermore, we can improve our context-free grammar to not be exactly context-free, but to be more linguistically motivated by, we'll improve the n-grams. Instead of being standard n-grams, word follow word, we can create an n-gram in the more meaningful space of head words. So what are head words? A head word is a linguistic concept. It says that if you take a sentence and you parse it, you get a tree, and you can designate, let me write it, the contract ended with a loss of 7 cents after. With a loss of 7 cents after. And then it continues somehow. Now I'm going to create a partial tree. A loss. $7 cents off, 7 cents and off, and loss here. So think about it as being produced by a context-free grammar, and think about every time you merge two words, one of them is chosen to be the head word, so represent whatever comes underneath it. Not just two words. When you merge any two non-terminals or terminals. So 7 cents will be represented by cents. Of 7 cents, I think, will also be represented by cents. No, it's represented by of. A loss would be represented by loss. And loss of will be represented by loss also.
Essentially, the dependency.
It is a dependency structure, yes. So head word is a concept that comes up a lot in dependency grammars. It's not mathematically well defined. It depends on the sort of linguistic theory. But let's try to capture just the intuition behind it. It does capture the dependency. So it says that the rest of the world depends on this part through this concept of. Or the rest of the world depends on this part. It doesn't matter so much if it said a loss or the loss. What matters is that it was a loss. I'll put the rest up. With and ended. I don't have room. Let me try to. Shall I go up to here? Nah, let's leave it here. So here, back to what I'm going to improve on the n-gram. I'm going to use a trigram, but instead of the trigram running here, in the surface form, it's going to run, take into account the head words. So I'm going to predict every word, let's say the next word that comes here, based on the last two, not the last two words before it in the surface form, but the last two exposed head words. The last two head words that have not been merged yet. So in this case, it will be based on this one and this one. Not a very good way to predict the word after. But maybe if I merge them further, it'll make more sense. So whether would it be a good idea? Let's say, all right, I'll do the example from the presentation. This is a work by Ciprian Scelba, who did his PhD at Johns Hopkins in the late 90s and moved on to Microsoft. So let's bring down the screen. So this is the example I was trying to give. And what I'm going to do now is assume that somehow you know the full parse. Okay, a little bit like the PCFG case. We're going to start with a case where you know all the hidden stuff. You know the full parse. And how would you calculate the probability according to the model of the entire full surface and hidden part? The first thing, there are three components to it. One component is assigning a part of speech. You see each one of these is assigned a part of speech. Remember, we're assuming that you know everything, that everything is fully annotated. The second component is the merging and the decision in each merge. So the merge is the reverse of the production. Saying the production produced these two from here. And what was the non-terminal that was in charge of this production? Was it this one or that one? So who was the head? So we're going to build the tree backwards. We're going to start from the words, add parts of speech to them, merge them up, and occasionally introduce new words based on an n-gram or on a trigram that looks on the last two exposed head words. So if the full annotation of the sentence was given, you could go through and multiply all of these events. The probability that the is tagged as a determiner times the probability that contact is tagged as a noun times the probability that this is tagged as this, and so forth all the way. And then the probability that these two came from this production with this head word, and that these two came from this production, and then the this and this merged into this, and so forth. You build the tree, and every step of building the tree has a certain probability, and you multiply them together. And the probabilities come from one of three sources, which correspond to the three colors. Either a part of speech assignment, or a merge, with a choice of which side is the head, or a trigram prediction, but not a regular trigram, a trigram that's based on the last two open head words. Okay? So, in principle, this corresponds to the case of the HMM or context-free, publicity context-free grammar of calculating. Oops. This corresponds to the case of calculating P of O and Q given the model. Remember that we started with that in HMMs and in PCFGs. In HMMs, this is simply multiplying A times B times A times B times A times B. 2T multiplications, straightforward. In context-free grammar, this is just going through the parse tree and multiplying the probability of each production. It's always simple, this case. The second part is, how do you do this? How do you calculate the probability of the surface form only? And that effectively means you have to effectively sum over things of this sort, but many, many of them. Right? That was our second part. We had it in HMMs, we had it in PCFG, we have it here. The third would be the decoding problem. How do you, given O, given the observables, how do you effectively go through the exponential set of all possible hidden parses and find the one that has the highest likelihood. And the fourth one, the hardest one, is how do you set the parameters of the model just given observables. Let me show you how the decoding is done.
Isn't there an extra problem here in terms of an HMM and a PCFG? What you're essentially trying to do is predict the latent structure given an observed output. Here, if you're using it as a language model, you also want to predict what the next word is going to be, right? How would you do that?
Well, the n-gram is trained the same way as the rest of it is trained. So there are going to be three components. There's going to be a para-speech tagger. There's going to be a dependency grammar merger. And there's going to be an n-gram that's based on the last two exposed head words. So how are we going to train it? Again, in complete analogy with the HMM and PCFGs, suppose first we had fully labeled data. Suppose somebody took the Penn Tree Bank, which they did, annotated every word with its part of speech, and on top of it put a dependency grammar tree on it that specified the non-terminal or pre-terminal for each node, and for each intermediate node that split tells you where the head word came from. Did it come from here or from here? Given this fully labeled data, training these three components is trivial. It's relative frequency. Right? Everything is fully labeled. Everything is seen. You just use relative frequency with some smoothing to train each one of the three components. For example, the trigram component, all you have to do is collect from your data triplets of exposed head word, and the next word that showed up. Right? Build a trigram. Relative frequency with some smoothing. So again, it's a complete analogy at the level of what the problems are and how they're solved. This problem is straightforward. This problem is on the surface exponential, but solved by dynamic programming. Decoding, same problem, same thing. On the surface exponential, it's the forward or Viterbi, forward and Viterbi. The same problem. The learning or training problem, split in two. Do you have fully labeled data that's labeled with all the latent variables, or not? If you do, it's straightforward. It's separable into three separate relative frequency estimations of the three separate components. If you don't have the labeled data, if you just have unlabeled sentences, now it becomes difficult, and now you need EM. So you start with some values and go through an EM procedure, which I'm not going to describe the details of. What I do want to show you is that some of the details of the decoding part. So here's the same fragment of a sentence, and let's say that you were gradually building the fully annotated tree with a sentence. And let's say we've gotten to this point. We got to a point here where the dependency tree does not do any more merging. There's no more merging to be done that's consistent with the full annotation. Remember, what we're doing here is the case of assessing. Okay, I'm not doing exactly the decoding. What I'm doing here is this. I'm going to be using then in a stack-based search to find the best path. But I'm going to follow, in the example, I'm going to follow one particular path, one particular annotation. So imagine that you have the annotation in your hand, and you are consulting the model to tell you what the probability is of generating that annotation. You got to here, and now you want to generate the next word. The next word, there's no more merging to do, so your context is a null context. You have to predict the word sense. you're going to predict it from the last two exposed head words. This is an exposed head word because it's not part of any merge. And the one before that is of. So you're going to predict it from an n-gram with a context of 7. If it doesn't make sense, I hope it will in a minute. After you predicted the word sense, you have to predict the particular part of speech tag of that word. So you call on the part of speech tagger with the word sense, and you ask it what is the probability that you assign to this particular tag, N and S. Then you want to account for this being merged through the dependency grammar with the word that came before it, and it's a particular merge that there are two kinds of merge. The merge that chooses the right child to be the head word, and a merge that chooses the left child to be the head word. So you can think of the adjoining operation as a stochastic operation that has a probability. It has some probability of choosing the right child, some probability of choosing the left child, and that's represented by this operation: adjoin, choose right child, and call the result NP, noun phrase. And then you merge further up. So you have another adjoin operation. This time the head word would come from the left and would be assigned the tag PP, prepositional phrase. And you keep going to the end. So here are the three models, and here's how they operate together. Think about it as a generative process. You start with the tagger. It tags the word, and then you pass control to the parser, and the parser decides how many adjoin operations to perform one after the other, where each adjoin operation can be either adjoin right or adjoin left. Once the parser decides to do no more adjoint operations, it passes a null to the predictor, and the predictor is the n-gram that predicts the next word based on the last two exposed head words. Once it predicted the next word, it passed it to the tagger to tag it, and so forth. So if you have fully parameterized predictor, namely n-gram, fully parameterized tagger, which you could implement any way you want, and fully parameterized parser. So if you have these models in your hands, think of them as probabilistic models, you can daisy chain them together and use them to generate fully annotated sentences. The colors correspond to the colors of the different components. So the blue is generation from the tagger, the green is generation from the parser, and the red is generation from the n-gram, the predictor. So this is just a way of expressing how you calculate this. Now, how would you use it to do decoding? In decoding, you have to go over all possible cues, all possible trees, and all possible part-of-speech assignments, and even all possible assignments of tags to the intermediate nodes, like here and here. The only thing that's constrained is the surface form, the words themselves. The way you go about doing that is very similar to the way you go about speech recognition, which is you build a stack of all possible partial parsers. So it can get to be very large. So every time you consult, let's say, the part-of-speech tagger for a particular word, let's say you're trying to consult the tagger for sense, well, you may find in your dictionary that there's more than one possible part of speech. So you have to add to your stack all possibilities, each with its own probability. And then you call the parser, it's a green, and the parser, one choice is to adjoin right and call it noun phrase, but maybe there's also a legal merge that adjoins left, or that adjoins right with a different tag here. You have to allow all of them, each with its own probability. So your stack will grow fairly fast exponentially, because the number of different parsers that are consistent with this partial sentence grows very fast. So you have to introduce some trimming, some pruning. So you have partial, those of you who have done speech recognition or have taken the class and know how it's done, you have partial scores, and you use heuristics to decide that anything that's not in the top 10,000 options gets trimmed out, or anything that's not within a certain distance from, the score is not close enough to the top score, gets thrown out. And of course, by doing that, you're introducing a search error. So the decoder here, unlike the decoder in the case of HMMs, the decoder here is not guaranteed to give you the best answer. There could be a search error. So there's a tremendous amount of detail in this, but what I'm hoping you'd get out of it is the analogy with the other two cases we saw of a latent variable model, the HMMs and the PCFG. The kind of questions that come up are these questions. First, this one, it's usually easily solvable, although in this case it's a big production, but it's doable. This one, either the evaluation of the sum or the choice of the one particular is done by dynamic programming, and in this particular case, even dynamic programming is not enough because the size of the stack is going to grow and grow and grow, so you need to do pruning, so it's not guaranteed to give you the correct answer. And the third and hardest is learning the parameters from unlabeled data, and for this you use EM. I can see how overwhelmed you are with the news.
So the POS tagger doesn't work without the dependency parser. So it typically works together with the dependency parser.
I'm sorry, what
Or is
word?
it just only one option? So I'm asking whether the POS tagger can work like alone, like decoupled from a dependency parser, or is it correct to say that they would typically be working together, like chained together?
They are chained together, but when you design the parser, the part of speech tagger, you could choose to make it consult nothing else. So the simplest parser would just look at the word and look up in the dictionary of dictionary that contains parts of speech, which parts of speech this can be. And if it has further frequency information, it might assign probabilities, otherwise it might be uniform.
So it should be like an HMM or maybe an n-gram.
It could be completely context-independent part of speech assignment. You just look at that word and say, this word, how likely is it to be a noun? How likely is it to be a verb? How likely is it to be whatever? A more smarter choice would be to say, when I consult, hello? Okay. When I consult this word to decide on the part of speech, I have access to the history. So what is the best distribution over part of speech I can assign to this, knowing everything that came before it? And that may make your part of speech tagger much smarter. So it would assign a sharper distribution, a more appropriate distribution, and maybe even a smaller number of choices, which would reduce your stack. Same is true for all the other components. The parser would typically look back quite far. The n-gram, by your decision, is a trigram, but you could make it a 4gram. You could make it, look at anything. Yes?
It seems like a really, really complicated way of basically just using the dependency parser as a language model. Can you just use that directly and not have to predict words in a linear sequence? That is to say, you don't want to predict the contract ended, but maybe ended first and then contract and then loss in some sort of
Right.
fashion.
Very good point. You certainly can. You could build a probabilistic dependency grammar. The one problem with it is that several problems. One is you cannot operate in a left to right manner. So if
The question is, do you need to?
well, if you are interfacing it to a speech recognizer, it is better if you could, although in reality, even speech recognizers usually don't use fancy models online. They allow a simpler language model to produce the top 1,000 possible outputs, and then they rescore those 1,000 outputs. So you don't really need to. I would agree with that. A second, more important component is that by having your own dependency grammar, you're bringing how are you training your dependency grammar is the question. If you have labeled data to train it, then this is not complicated. Then
Isn't that the same case for the parser and the part of speech tagger that you're using? You need labeled data to train them in the first place.
But you don't need labeled data because you can use EM here. If you have labeled data, then you can train them absolutely, each one separately. And you can think of a probabilistic dependency grammar that does not use an n-gram component, and it just does everything by production of the dependency grammar. The problem is, all these, I started with this motivation, all these more linguistically meaningful models are not very good at the lexical level of predicting actual words. Take a context-free grammar. It's a wonderful way to explain, I ate pizza without anchovy, I ate pizza without hesitation, but I ate pizza without a hammer. What's the difference between hammer and anchovy? I mean, these grammars don't know what they're talking about, right? They know if it's a noun or not a noun. You can make a distinction between animate noun, not animate noun, edible noun. I mean, you can make finer and finer distinctions, but at the cost of growing the number of production success of the grammar exponentially. The one thing that n-gram does that is very hard to beat otherwise is it really knows words. Because it's really good at correlations between two adjacent words. That's what it knows. That's the only thing it knows. Correlations between the adjacent words. So it's the most lexicalized of all models. N-grams are just fantastic lexicalizers, if you want to call it that. You can take huge amount of data and work out correlations between two adjacent words, three adjacent words, and use that to great benefit. When you come from the other side, when you come from the direction of linguistically meaningful theories and grammars and stuff, you're very good at the big picture, but terrible at the local picture of specific choice of words. For example, just about anywhere that the word large fits in a grammar, the word big fits in a grammar. But it doesn't mean that people actually use large and big interchangeably. They might not. An n-gram would know that. But most grammatical grammars, real grammars, will not. So that you can think about them as having complementary strengths. So back to your question, if you're thinking of using just a dependency grammar and training it, that's fine, but I don't think it will perform well at the lexical level, and that's where most of the juice is. If your goal is to understand what was said,
except that dependency sort of
has
the relationship between words directly rather than through a latent structure.
Yes, so you can say that dependency is a lexicalized, it's a highly lexicalized grammar, right? And you can think of other grammars that are highly lexicalized. What's the name of the grammar that Dennis Slater invented here? Link grammar is another case of a lexicalized grammar. And the tree adjoining grammars, there's lexicalized versions of those. And for a linguistic understanding, you don't need the lexicalization so much. But for accuracy of either word recognition or, I guess it depends what it is. Definitely for speech recognition, you do need the lexical identities, otherwise.
So how does this model perform?
It does perform better than, so let me show you the results, than an n-gram. And interestingly, I think I mentioned to you that the most common story in trying to improve on models of language is you work for a couple of years, you devote your life to it, and at the end, it doesn't quite work. And then you mix it with a trigram, and then it works, right? So that's exactly what happened. Let's go to his results. So here's the language model. Here's a baseline, just a plain word-based trigram. Remember, he used EM to estimate all the parameters. It turns out that just EM by itself will give you terrible results. I warned you, EM is not a panacea. But he did what I tell you always to do, is manually label at least a small amount of data, train a standard relative frequency model from that, and then use that as the seed to train on much larger amount of data that you cannot afford to label. Okay? That's exactly what he did. He basically seeded it with data from TreeBank, which is fully labeled. And then he ran his EM algorithm starting from that and re-estimated the parameters using the EM method. Here's performance in terms of perplexity on the development set. L to R means left to right perplexity. Here's performance on test set. This is the baseline. Not better. In fact, a tiny bit worse, not significant. And after re-estimation, better, but slightly better. I mean, better, okay, somewhat better. I wouldn't, you know, give up on this. This is hard to get. And then the usual trick, interpolated with a standard trigram, the same trigram that was the baseline. So here, of course, there's no difference. And here, lo and behold, it's better, and this is even better yet. So 148 to 167, 20 out of 160, 12%. That's significant. In fact, that would result in 5 to 6% reduction in speech recognition error rate, typically. So it's not, you know, changing the face of the field, but it's enough to get a thesis for sure, which is what I got. I hope you know that you're guaranteed that these are going to be no worse than this, right? So when you interpolate with something, you're going to be at least as good as any one of the components, as long as you choose your weights based on held out data. Malcolm.
Thinking with like interpolation, that it reminds me of the whole bias variance trade-off that we started off with when we were talking about interpolation originally. And I was thinking that could you expand that idea to having a sort of trade-off between like small scope with good lexical understanding versus a big scope with good sort of like macro language understanding? Yeah,
it's a very nice question. This is really the name of the game in just about any problem in language. You often deal with this. I have a little bit of data about which is just in my domain, or it's labeled, or it's really great. And then I have increasing amounts of data, often increasing by orders of magnitude, that are not labeled, they're not exactly in my domain, they're older, and then which one should I use and how? And my answer is you typically want to use both. And how is you don't want to mix them together, that's for sure. Either you start by seeding with one and then retraining something like EM with the whole thing, or you build a separate model from the small high quality and one from the large lower quality and you linearly interpolate them. Or you build a small one from the high quality and then you train a smaller number of features in an exponential setup that's based on the larger one. Or something else I didn't think about, but it's a very commonly encountered situation. Any final comments, feedback, thoughts? I mean, we'll still see you next week, but we'll be rushed. Not that we're not rushed now.
Is there any benefit combining of the dependency grammar? Well, like a standard, for example, context-free grammar with the ES tagger. Are there any examples that, like, how much could you gain by combining the two models? So, because you probably also lose a lot in the tagging speed, I guess.
In the speed, you're saying?
Well, yeah. What are the trade-offs?
Yeah.
Throwing in, like, combining more models, and how much do you lose in terms of speed?
Yeah, that's a fair question. You can certainly vary on the story that I described here, use a context-free grammar easily, use different levels of complexity of the part-of-speech tagger. It was just an example of how you combine all these partly linguistic, partly statistical, sort of partly lexical, n-gram-like, and partly linguistically inspired models. All right, I will let you go. I will see you here on Monday. To remind you, everybody should be here. Please come early because we're going to be very tight on time. And if you don't want to be recorded, just send me a short note or call me or stop by or whatever.